Okay, today we are going to discuss about a topic which is imperfect bifurcation and catastrophe. Okay, so far we have seen different types of bifurcations, and lastly we have seen a pitchfork bifurcation, which was having this following form where x dot is equal to Rx minus x cube, right? So, and in the bifurcation diagram we have seen that the curve is perfectly symmetric. Okay, but now if you see in the real world, we will not have such a perfect symmetry system. Okay, there will be some imperfections. Okay, so we are going to in today's lecture we are going to see the systems with some imperfections in that perfect bifurcations. Okay, so in this pitchfork bifurcation, where this is particularly a supercritical pitchfork bifurcation, and here I am going to introduce a little parameter to make the perfect symmetry system into a unsymmetry. Okay, the symmetry will be broken by introducing this following parameter, which I'm going to denote that as h. Okay, where this h is known as imperfection parameter. Okay, now if h is equal to 0, then we know that that's a pitchfork bifurcation. But what if h is not 0? So how the system is going to behave? Okay, what sort of bifurcation we could observe? So that's what we're going to see today. So for this system, the first thing we will do is identify the fixed points, right? So let's try to identify the fixed points. Okay, so x dot is equal to 0, which gives me h plus Rx minus x cube equal to 0. Okay. Now if you see, this equation is actually a cubic equation. Okay, I could not reduce into a simpler form because h is no more a 0 value. Okay, so maybe it's difficult for me to proceed further with this form. So what I'm going to do is I'm going to use a graphical approach, which we have done for various other examples. So for this, what I'm going to do is this f of x, which is this term, right, which I'm going to consider that as g1 of x minus g2 of x. Okay, where g1 of x is equal to Rx minus x cube. Okay, and g2 of x, which is equal to minus h. Okay, and when these two things, when g1 of x minus g2 of x goes to 0, then those points are fixed points. Okay, so for that, what I'm going to do is I'm going to plot g1 of x and I'm going to plot g2 of x. Okay, and then whenever those two things intersect, then those points are fixed points. Okay, let's plot it and see. Okay, so this is g1 of x. Okay, and that's g2 of x. Now those two things, for some value of h and some value of r, they intersect. Okay, so actually right now the system is having two control parameters, one is r and another one is h. Okay, now let's say for some fixed r value, let me just change this h value and see whether any surprise behavior is going to happen. Okay, and if I change, there is no change in the number of fixed points, still the number of fixed points are just 1. Okay, fine. So maybe I will increase my r value, and for a different r value let me change my h value. Okay, so if I do that, let's say if I maybe increase the r value, maybe a positive value. Okay, if I make the r value to positive, I am having this sort of behavior. Maybe at this time, if I increase my if I change my h value, then still fixed point is 1, but at a certain range, if you see, there is 2 more points where it gets intersected, right? So in addition to this fixed point, I am having 2 more fixed point, right? The behavior is somewhat similar to the pitchfork bifurcation, right? So when r is positive, I am observing a bifurcation due to the change in h. Okay, and now let's see, for a given r, what is the critical h value. Okay, because h is this some h value around minus 0.8, for this 1.6, near to that I am observing some bifurcation. Suddenly new fixed points are emerging, and also if you see in this region 2 fixed points, and after I increase further, again it becomes a single fixed point, which is just this point, right? So let's see, let me try to identify this point and this point where the bifurcation is happening. Okay, that's what I'm going to that's what we are going to do now. So let's say my bifurcation is happening at this point where the slope of this g1 of x and g2 of x are same. Okay, let's first identify when those two slopes will match. Okay, so this is g1 of x and this is g2 of x. The slope of g1 of x, which is g1 prime of x, which is equal to r minus 3x square. Okay, what about g2 prime of x, which is, this is just constant, so it's 0. Okay, so yeah, so whenever this slope of g1 of x goes to 0, then the critical the bifurcation is happening. I mean, that's reasonable, because if you see the figure, it's happening at this point and this point where the slope of g1 of x goes to 0, right? Okay, let's calculate. So in that case, r minus 3x square goes to 0, and it will go to 0 when my x value is plus or minus square root of r by 3. Okay, r by 3. Okay, so that's the point. Now let's impose this condition when the points are intersecting, okay, which means the f of x is 0. And if I impose that condition, what do I get? So 2 no, so minus h is equal to r, but in the place of x I am going to put this one, so root r by 3, then okay, this one minus a cube of this thing, which is r by 3 into root r by 3, but I have to consider this 2 solutions, so I am going to do plus r minus, okay. Or instead what I could do is I could write whatever inside the bracket, modulus of h, okay, so that I could consider both plus and minus, which is equal to r, or let me simplify this, so 2r by 3 into root r by 3, okay. So this is my critical value, so h, so hc, so that's our critical value, okay. Now we have identified the critical value. That critical value, that bifurcation, where the bifurcation occurs, actually depends on the r value. And from this picture we could see why there is no bifurcation occur when r is negative, because when r is negative, square root of a minus number has no meaning in the real axis, okay. So therefore bifurcation occur only for r which is a positive value. Okay, so let's plot this picture, the curve r versus hc, okay. Okay, so now this one, so this is the curve, okay, where this axis is r and this axis is h, okay, and this curve represents when h is equal to hc, okay, and this curve is known as bifurcation curve, okay. So this tells for a given r what is my hc, fine. And if you observe that there is this point which shows a common tangent between these two different curves, okay, and this set of behavior is known as cusp, okay, fine. Now the question is, so these are the lines where the bifurcation is going to occur, but when it occurs, the number of fixed points are going to change, right? So here we have observed that the 3 fixed points are at one point there were 3 fixed points, and at another point there was only 1 fixed point, okay. So this curve actually distinguished the region in the control parameter space such that in one region there will be only one fixed point, and in another region of control parameters there will be three fixed points. Okay, let's identify which region gives three fixed point. Okay, let's say so this is my h. So when h is equal to 0, my r value is positive. At that time it's just like a supercritical pitchfork bifurcation. At that time when r is positive, I will have three fixed points. So this region is actually having three fixed points, and this region is having only one fixed point. Okay, so that's what this this particular bifurcation, this is not bifurcation diagram, but this is a bifurcation curve, and this diagram is known as stability diagram. Okay, so where we just plot it in the parameter space, control parameter space. Okay, fine. So one thing is, even though it's called a stability diagram, we do not know among these three fixed points which are stable and which are unstable. All it says is how many fixed points in this region and how many fixed points in this region, and this acts like a boundary between this region and this region. Okay, now let's do a bifurcation diagram for this system. Okay, so in bifurcation diagram we will plot the fixed points versus a parameter, but right now we have two parameters. So what we are going to do is we are going to fix one parameter and we are going to plot it with other parameter. So now at first we shall fix one parameter which is h. Okay, and then let's see how the fixed point is going to change with respect to r. Okay, so let's do that. So if I keep my h value to 0, okay, and this is the bifurcation diagram I will get. Okay, and if you see that bifurcation is a pitchfork bifurcation. Okay, now let's say I'm making a little imperfection, which means I'm going to change my h value, and let's see how that bifurcation diagram is going to change. And if you see here, I have made two plots. One is this one and another one is this one to represent this line, because just this curve is not able to capture this line as well. Okay, but let me change my h value. Let me slightly increase my h value. If I slightly increase my h value, see, I'm getting this curve and this curve. Okay, so that's my bifurcation diagram for some positive value of h. Okay, so if you see, this is almost like a pitchfork bifurcation. So because in pitchfork bifurcation we were having this line and these three branch of the curves were acting like a fork, right? So it's almost like that, but there was a slight unsymmetry. Okay, so that's what this imperfection, due to this imperfection parameter. Okay, so we are getting these three branches. Now out of these three branches, which is stable and which is unstable? Okay, once again let's see the pitchfork bifurcation. Okay, in the pitchfork bifurcation, if we see this line is stable, okay, in the supercritical pitchfork bifurcation, this will be stable, and that stable fixed point will become unstable, and these two branches will be stable, right? And this, it will be not different. Okay, so if we had an imperfection, this branch will be stable here, and it will continue to be stable in this side as well. Okay, and this will also be stable, where from this point this branch, okay, will be unstable. So that's the imperfection in the supercritical pitchfork bifurcation. If you see it in this book, if we see it in this book, the bifurcation diagram will look like this. Okay, so where this branch we observe an unstable, therefore we have represented in this manner, where this branch and this branches are stable. Okay, fine. So that's a bifurcation diagram for a fixed h value. Now what we are going to do is, for a fixed r value, how the behavior of the system is going to have, how the bifurcation diagram looks like if I vary with respect to h. Okay, so let's see that. So right, so this is going to be my bifurcation diagram for some negative value of r. Okay, where here this is this axis is h, and this is a fixed points, or x axis, where this curve represents for that particular h what is the fixed point, and that is valid only for this particular r. Okay, now if you see, there is no bifurcation is happening, right? For all value of h there is only one fixed point, but let's increase my r value, because we have observed that there is a there is a bifurcation when r is greater than 0. So let's raise this r value to greater than 0. If you see, and beyond r, if you see, there is a bifurcation which is happening at this h value, and also there is sort of bifurcation which is at this h value. Okay, so this is how we will have a bifurcation diagram when for a fixed r and changing the h value. Okay, so here if you see which branch is stable and which branch is unstable, actually this branch, okay, that's a stable, and similarly this branch is stable. Okay, the piece in between from this point to this point, that's unstable. Okay, and if you see the bifurcation diagram in the book, so it will look like this. So this branch is stable, this branch is stable, where this branch is unstable, and such a thing will occur only when r is positive. When r is negative, there is no bifurcation. Okay, so well, that's a bifurcation diagram for a fixed r value. But if you are wondering how can I visualize for both h and r as a parameter, so in that case I have two parameters. So if I have to plot it with both x as a function of h and r, then I will have to plot it in 3D, and I will get a 3D surface, and the 3D surface will look in the following manner. Okay, so this is the surface where each point in the surface represents for that particular r and h value what is my x value. Okay, and this is the point where r and h are 0. Okay, and if you see, this is how the surface looks like. And one more thing, if you notice, when I make a projection of this surface in this RH plane, then I will observe the curve like this, which is nothing but the stability diagram, right? So we have observed that two branches which are making a cusp at this point. So that's this picture, which is nothing but the projection of this surface. Okay. And one more thing we can observe, which is an interesting behavior in this system, is which is this jump. Okay, so we have observed a jump behavior when we observe a system with x to the power of 5, right? Even here we observe such a jump or hysteresis behavior. Okay, for example, let me explain that from this picture. Okay, let's say I have some h value for some r value, okay, such that my system is at this point. Okay, my system is stable at this point, and say I am reducing my h value. Okay, I am reducing my h value, so it's going to go in this and follow this branch, and once I reach this point, and suddenly there will be a jump. Okay, there will be a jump, and I will have totally a different stable fixed point. Okay, and then if I further decrease my h value, I will start following this branch. But when I start increasing again, okay, then I will follow this branch back, but at this point I will not jump over here. Instead, I will just follow this branch. Okay, and I could only go to this branch once I reach this point, and then I will once again jump. Okay, so that's how we could observe the hysteresis. I mean, there will be a hysteresis behavior for such a system. Okay, so that's what this picture explains. If I start from here, okay, there is a jump, and it will start going in this direction, and when I start decreasing, then I will go somewhere here, and then after I reach here, I will jump suddenly, okay, to this side of the surface. Okay, but that sort of jump will not happen when my r value is negative. Okay, it will just follow this single curve. Okay, right, and this behavior is termed as catastrophe. Okay, the reason it's been termed as catastrophe is because in a physical system, if we observe, there is a sudden change in the equilibrium point or fixed point, and that's bit danger when it comes to the for example, for a structure. Let's say the system is at one particular configuration, and suddenly there is a jump at some other configuration due to the slight change in the control parameters. So such a behavior is unacceptable for some physical structures, and therefore such a behavior in the dynamical system is termed as catastrophe. Okay, so yeah, so that's all about this imperfect bifurcations and catastrophes. And in the next lecture, we will see one example, one physical example where this bifurcation behavior happens. Okay, thank you.